Okay, sir. Right now, we are live now, and
Okay.
this platform is your. Thank you, sir.
All right. So I will share my PPT now.
Yes, yes, definitely, sir.
Yeah, just make sure that it is visible to you. So I think I can do screen sharing and then it
Yes,
should
you
work,
can.
right?
Both are available, but you can go for the screen share, sir.
Okay.
Yes, I
So
had
now if
to
I
in.
open my PPT
Yes,
and make full screen, then it should be visible to you as a full screen, right?
yes, it's absolutely visible, sir.
Excellent.
Yes, you should start now, sir.
All right. I think my microphone is not working, so I will just use my laptop microphone and sound.
No worries, sir. This is the one-way platform, so you
Okay.
can just use anything else.
Okay. So my voice is clear, right?
Yes, definitely, 100% clear, sir.
Excellent. And are the students already there now?
Yes, students are already present here.
Excellent. I just want to know if these students are all from organic chemistry background or are they mixed?
No, it's a mixed students from the
Okay.
computer science, library science, life science also, and chemistry. There are the all types of students are available, sir, here.
Okay. So it should be a general talk then.
Yes, it's a general
Okay.
talk. Like,
Okay. I have prepared one for science, but anyway, I can talk about myself and how I came about. Might be more interesting for the students.
yes, sir, definitely.
Okay.
Okay, okay.
Okay.
Thank you, sir.
Yeah. All right. So I welcome all of you to this talk. My name is Dr. Sachin Kumar Modha, and I am currently working as assistant professor at Tarsadia Institute of Chemical Science at UCA Tarsadia University. Uh, I did not know whether the crowd will be from the general science background or specific from chemistry. So the talk that I have prepared is basically for chemistry. But instead of going through this talk, probably I can give you a more general talk because the crowd is, I think, from the different backgrounds. So let me first introduce myself to all of you. As I said, my name is Dr. Sachin Kumar Modha, and I was born and brought up at Porbandar. So Porbandar is quite close to Junagadh, as you all know. And my journey so far has been quite interesting, and there were ups and downs, as it is case with I think almost all. So in 12th science, I failed in four subjects, namely physics, mathematics, and chemistry. We had two papers of mathematics. So in the first attempt, I only got like 15 marks in physics and 22 in chemistry and similar in mathematics. In the second attempt, I only attempted these four subjects, and I got 35 marks in physics and only 27 in chemistry. And I was given 8 marks as gracing to pass me. So I passed chemistry, we can say, with gracings. And then I did my bachelor's at MD Science College, Porbandar. You might have heard this name of the college, Maharshi Dayanand Saraswati Science College. I completed my BSc there, but interestingly, I did not want to take chemistry at that time. I wanted to take physics or mathematics. But in the third year, the physics was not there, only chemistry option was available at the college. So I took chemistry not by choice, but by compulsion, you can say. And I completed my BSc with 61% marks, and it was in Gujarati medium. Then I moved to Rajkot, Saurashtra University for my masters. And interestingly, there also I only got as a second last student admission in the classroom of 80 total students. I completed my masters there with English medium in 2006. And interestingly, English medium somehow suited me, and I got second rank in the university in chemistry. After masters, I wanted to do a PhD, but there was no vacancy under Professor Anamik Shah sir, and I wanted to do my PhD under his guidance. So I went for a job for some time until I get a PhD admission under his able guidance. So I went to Oxygen Healthcare. It was a CRO, contract research organization, and I worked there for 1.5 years, and then joined a group of Professor Anamik Shah for my PhD for my PhD. Uh, During my PhD, within 6 months, there was an opportunity because of collaboration of Professor Anamik Shah with one of the professor in Belgium. His name was Professor Eric van der Eycken. So he wrote an email to Professor Shah that there is a vacancy for a PhD student, and if somebody would like to come there for a full-time PhD. And Professor Anamik Shah sir sent me to Belgium. I had to pass one exam there, uh, and if I get more than 70% marks, then only I could continue my PhD there in Belgium. Otherwise, I had to come back to India. So, with help of Professor Anamik Shah sir, I took this risk and went there. I did study for around 11 months and continue my research work also at the same time in the group of Professor Eric van der Eycken at University of Leuven, which is close to Brussels in Belgium. And in 2009, I passed the exam for pre-doc and enrolled into full-time PhD program. And during my pre-doc, I was getting a fellowship, and also during my doctoral studies, I was getting fellowship from the project of Professor Eric van der Eycken. So it was quite interesting journey, I would say. And I completed my PhD in 2012. There was, of course, a lot of facility there. The university is, I think, 45th ranked in the world right now, and it's a 600 years old university that is in Leuven. So because of all these facilities and able guidance of Professor Eric van der Eyck, and I could do my PhD with a lot of publications, and high impact journal articles came out as a output from my research work. In 2012, I completed my PhD, and then I moved to University of Manchester for postdoctoral research. There I worked for around 2 years in the group of Professor Michael F. Greene at University of Manchester. University of Manchester is also highly ranked university. I think it is around 48th ranked in the world. And during my stay there, I applied for Alexander von Humboldt postdoctoral fellowship to work at Technical University of Munich in Germany. So I got that fellowship, and then I moved to Munich in 2016 for 2 years to work with Professor Thorsten Bach at Technical University of Munich. So TUM is also a highly ranked university. I think currently it is 29th ranked in the world. And I enjoyed working there in the field of photochemistry, uh, which was quite different from my previous experience of PhD and postdoc, I would say. So I worked there for like 2 years, completed one of the projects that was given to me, and then my stay was extended by 1 year with help of Professor Thorsten Bach to complete the work that was going on. And in 2019, I came back to India, and since then I'm working at UK Tarsaliya University as assistant professor. And currently there are around 8 students registered under my guidance for PhD. 2 have already completed, and 8 are currently pursuing PhD. And I'm really enjoying teaching, I would say. So this story was, I think, necessary in the beginning to introduce myself and to also show that failure in 12th did not hamper, I would say, my career. Probably it helped even to guide me towards the right direction. And the subject that I passed with second attempt with Cressing chemistry, I did my PhD from a foreign university in the same subject. So this could probably inspire many of you. So I think failures are sometimes necessary so that we can learn from them and improve ourselves in the right direction. All right. So with this introduction, I think it is better if I, rather than giving you a chemistry specialized lecture, I rather give you a general lecture, and I might have some presentation for that. So let me just open that and share with you again. All right, so I think we can probably talk about more general topic that is more related to electromagnetic radiation and how they are generated, and how what are the characteristics of electromagnetic radiation. Because electromagnetic radiation is, I think, not only in the chemistry field, but it is mainly in the physics field, also in engineering, even computer. So let's talk about that in general rather than being more specific about chemistry. All right. So, so this was this topic was about, of course, spectroscopy, which is generally broadly used in physics and chemistry. which is branch of science to study interactions of electromagnetic radiation with matter. And electromagnetic radiation, in short, is called EMR. So when we talk about EMR, generally this visualization comes to our mind where we see two components, magnetic and electric, and then they are perpendicular to each other and they are moving in a perpendicular direction. But what is electromagnetic radiation? Do we understand it in terms of basics of it rather than just a visual image that we memorize? So let's try to understand that. So how does the EMR form? That's the first question that might come to our mind. कि जो ये विद्युत चुंबकीय तरंग है वो कैसे उत्पन्न होते हैं? So to understand these concepts, we first have to understand the concept of charged particle. Charged particle can be represented in two manners, one with a positively charged particle, another as a negatively charged particle. So what is the meaning of positively charged and negatively charged particle? So when, let's say, a particle has electric field lines coming out of it towards outside, that is considered as a positively charged particle. And when a charged particle has electric field lines coming into it, it is considered as negatively charged particle. So these particle does not necessarily mean a molecule with a charge, right, or atom with a charge. We are talking about subatomic particles like positron, negatron, gravitrons, and so on. And because of this reason, you see, when a positively charged particle comes closer to a negatively charged particle, they complement each other. So the electric field lines that are coming out of the positively charged particle enter into the negatively charged particle. And because of this, they have attraction with each other. While when you consider two same charged particle, let's say positively charged particle, then they repel each other because they are not complementary to each other. And that's why there is a repulsion. Same applies to the negatively charged particle. So you might be wondering why I'm talking about charged particle here when we want to understand, let's say, electromagnetic radiation. So this is because let's watch a video to understand this. So in this video, we will try to understand how electromagnetic radiation forms from a charged particle. Let's consider one positively charged particle here. So obviously, it has an electric field that is applied outside of the particle, right? Electric field lines are coming out from the particle. And if it is a stationary, then there is no phenomena happening. But if there is a movement in this particle, let's say in one direction, then movement of electric field, of course, as you know, it can create a magnetic field. And movement in magnetic field can, of course, create new electric field. As we understand from, let's say, movement of current in a wire, there is a magnetic field around the wire that is having a current. So these two fields have capacity to generate each other if there is a movement. So when there is a movement, of course, electric field creates magnetic field again creates electric field, then electric field creates magnetic field. So they create each other. And then there is a movement in one direction of these fields when they are creating each other. Basically, this is electromagnetic radiation. So simply putting, electromagnetic radiation is formed from a particle, right? When it moves, when there is acceleration in the charged particle, electromagnetic radiation forms from this particle. Now, if you want to correlate the energy of these waves, electromagnetic radiation, with particles, of course, you can correlate with the vibrations of the particle. More the vibrations of a particle, higher energy electromagnetic radiation forms. Lower the vibrations, less energy electromagnetic radiation forms from these particles. Now, these, of course, these waves, the spectrum that we call, has various components. One is visible, another is IR, UV, microwave, X-rays, radio waves, and gamma rays. So as you go from left to right, the energy increases, right, from radio waves towards gamma rays. So energy and wavelength have an inverse relationship, as we already know, for the electromagnetic radiation. Visible radiation we use for a lot of purposes like CCTV camera, television, even other electromagnetic radiations are used for, let's say, micro apparatus, satellite communication, even observing the universe. Of course, we need to study electromagnetic radiation, and through them, we can study the whole universe. Right? For example, we study planets, stars, galaxies, the whole universe. So then information about the universe comes to us through electromagnetic radiation. Now let's try to understand relationship between temperature and electromagnetic radiation. So if, let's say, a particle has vibrations, the vibrations are nothing but temperature, right? So if material is vibrating, that means it has a temperature, or temperature is basically means vibrations. So let's say if there is a tea or coffee that is at certain temperature, there are certain vibrations in those molecules, right? Might be small. If you increase the temperature, the vibrations within the molecule also increase with temperature. And if you increase temperature above certain limit, then at certain point electromagnetic radiation starts to come out from these vibrating particles. So basically, temperature has this relationship, you can say, when we talk about formation of electromagnetic radiation. So let's go a bit more general now from this point onwards. So for us, let's say the biggest source of electromagnetic radiation is sun, right? For example, I'm talking right now. I'm using energy stored in my body to talk to you. That energy I have received from food that I eat, right? And in the food, the energy is of course coming from the plants or vegetation that the food grow from. And in the plant, the energy is stored through sunlight via photosynthesis. So basically, when I'm talking right now, I'm using sun's energy to talk. Similarly, let's say if a fan is running in your room right now, or you're using an electric device, that electric current is generated at some geothermal power plant where coal is burned to generate current. In the coal, the energy is coming from, of course, again, vegetable that was in the soil for many years, right? And again, the energy in those vegetations is coming from sun. Similarly, if you are driving a bike or a car, you are using petrol or diesel, that is coming from petroleum. Petroleum also ultimately is product of living organism that was buried in the soil, in the ground for many years, right? And in those, again, the energy is coming from sun. So basically, we are using sun's energy in almost all aspect of our life. Even apart from this, when we see through our eyes, of course, the electromagnetic radiation that is coming from sun, because of that we are able to see, right? Vitamin D synthesis that happens in our body due to sunlight, right? So energy is coming through electromagnetic radiation for vitamin D synthesis in that sense. Even the rain cycle that is happening on the earth is happening because of sun's energy. The ocean is warmed up due to IR radiation coming from sun. The vapor goes to becomes clouds, and clouds bring rain. Even wind are created because of sun, right? Temperature difference brings colder uh, air towards the hot region, and hot air is going up due to temperature rise due to sunlight. So many things that happen on this earth are because of sun's energy, and that energy comes to us in the form of electromagnetic radiation. So let's try to first let's divide electromagnetic radiation in basically three components, right? First of all, how it forms in the sun, how it travels to earth, and then what happens when it reaches earth. So first of all, what how is it formed in the sun? Let's talk about that. So as we know, sun is like 1.3 million times bigger than the earth, right? It's huge star. And there is a particular process going on because of the material present on sun, that is hydrogen, right? So sun is made up of hydrogen, and the temperature of the core is 15 crore degrees centigrade. It's a huge temperature, right? 15 crore degrees centigrade. And at this temperature, only one fusion reaction happens, that is hydrogen converts into helium. Further fusion does not happen because this temperature is not enough. Right? 15 crore degrees centigrade is not enough for further fusion. So in our sun, only hydrogen is converted into helium through fusion process. And in this process, there is some surplus energy when the fusion takes place. You might have studied it in 12th or 11th. And this surplus energy comes to us in the form of electromagnetic radiation. Now, of course, the light that travels from sun to us reaches here within 9 minutes, but it is not formed at that point, right? Before 9 minutes, it is formed within the core of the sun, probably 3 to 5 thousand years ago. And it takes around 3 to 5 thousand years for that electromagnetic radiation to reach the surface of sun from the core, and then only it is able to reach earth within 9 minutes. So again, another question arises from this, that if the sun can only form helium, then from where the material that we see on earth comes from, right? For example, water in my body, from where did it come if the sun did not produce it? So you can simply say that the material that you see on earth was produced even before the sun was formed, right? There was a huge star probably in the place where our solar system is right now, a huge star, probably 200 times or 1,000 times bigger than our current sun. And when a huge star, uses its fuel, that was hydrogen, it becomes colder from the outside and it is hot within the core. And because of this reason, it starts to swell and it gets bigger and bigger and bigger and becomes a red giant at some point. And then, due to high temperature in the core and low temperature outside, there is a blast happening, and the outside layer just is blasted away. That is known as supernova explosion. And in this supernova explosion, the temperature reaches quite high. Right? It can go in billions and billions of degrees centigrade within the second. And supernova explosion produces energy that is equivalent to our sun's energy that is produced in the lifetime of the whole sun. Right? So supernova explosion is huge explosion, and during this period, the temperature, as I said, goes very high, in billions and billions of degrees centigrade. And at this temperature, further fusion process happen further from iron. Right? So up to iron fusion can happen within a star, up to 8 billion degrees centigrade temperature. But after iron, the fusion does not happen in any star, irrespective of its size. So the elements that we see on Earth that are after iron in the periodic table are formed in the supernova explosion. So when these debris of supernova explosion, just scatter around, after certain period of time, they also, form smaller stars or smaller planets or fragments, you can say. And this waste that is generated from supernova explosion has a capacity to generate several stars and several planetary systems around those stars. So from that debris, our sun was produced, right? So hydrogen was accumulated through gravitation, and then sun formed slowly, the preliminary sun. And then the debris that were around that sun, due to gravity, they started to rotate around, or rotate around that preliminary sun. And then when sun reached a certain, you can say, volume, it started the fusion process at certain temperature, and then hydrogen started to fuse into helium. All the debris that were rotating around the sun, heavy debris came closer to sun due to gravity, and they made 4 solid planets, rocky planets as we call it, right? So you can say Budh, Shukra, Prithvi, Mangal. All these 4 are rocky planets. And the material that was less heavy, gaseous, it remained bit away because they had less gravity pull, being gaseous in nature. So these material formed 4 supergiants, you can say, planets, which we call Jupiter, Saturn, Neptune, Uranus. Not in this sequence, but they are gaseous giants. And interestingly, water that was formed remained liquid on Earth. The closer planets had very high temperature and water just evaporated from there, while the distant planets, gaseous planets, are colder. And because of that, water probably is frozen in those planets. So only on Earth, water remained in liquid state. And then, of course, probably you already understand how the life was created on Earth. And then, of course, through several billion years, 4.5 billion years, today we exist due to several evolutionary stages. So basically speaking, we are made from stardust, right? This is a famous quote from, I think, Carl Sagan or someone who says that we are made up of stardust, and it is true. So the material that we see on Earth, almost all of it is formed even before the sun was formed, right? Interestingly. All right, let's come back to the topic of electromagnetic radiation. So now we understand how electromagnetic radiation forms in the sun. Now, how does it travel to Earth? So electromagnetic radiation does not require a medium to travel, right? For example, sound, right now I'm speaking, it requires air, right? Through air only it can reach somebody's ear, and then they can hear what I'm speaking. So sound requires medium. But electromagnetic radiation does not require a medium. It can even travel through empty space, because electric and magnetic components are just able to generate each other. So they don't require medium to travel. Another thing, their speed is constant, right? It is 300,000 kilometer per second, like 3 lakh kilometer per second. So that speed is quite huge, right? It's quite fast. And interestingly, Einstein had said that Even the time is relative, but the speed of light is constant, right? Of course, we have to go into theory of relativity or general theory of relativity to understand all these things, but we don't want to go into that direction right now. But time is relative and speed of light is constant, or speed of electromagnetic radiation is constant. So when we talk about the whole spectrum of electromagnetic radiation, whether it is radio waves, whether it is visible range, whether it is gamma rays, they have same speed, right? But of course the energy is different based on frequency of that particular electromagnetic radiation. So because of this reason, the electromagnetic radiation is able to travel from sun to earth, even though there is no atmosphere in between, though material in between, right? Now when the electromagnetic radiation reach earth, some protection was required for life to form, right? Because high energy radiation can destroy molecules, like gamma rays can destroy molecules. So Earth's magnetic field is the first protection, you can say. Then the ozone layer and other layers that are there in the atmosphere outside uh, the Earth, they are filtering harmful electromagnetic radiation, and only a limited amount of non-harmful radiation is allowed to pass through, which reaches us, and then several processes can happen on Earth, right? So this was about how it travels, right? The characteristics of electromagnetic radiation. Then what happens on Earth when it reaches Earth? We have already talked about, I think, all these things, that photosynthesis takes place in the plants or organisms that have chlorophyll in them. So chlorophyll is, of course, a molecule, organic molecule specifically, and it has a magnesium metal in the core of organic molecule, which is able to act as a catalyst and allow photosynthesis using water molecules, CO2 in the air, and convert these molecules into glucose with energy of sun. So basically speaking, the energy of sun is stored in the form of chemical bond in the plants. And when we consume, or any animal consume that vegetation which has this glucose stored in it, our body or any animal body breaks down glucose through biochemical pathways and retrieves that energy that was stored in the form of chemical bond, and probably stores in the form of ATP, adenosine triphosphate, in our body. And then that allows to drive almost all the biochemical processes that happens within our body. So this is how the electromagnetic radiation energy that was stored in plants reaches us, right, in through various biochemical processes, and then we are able to use it for daily aspects. So electromagnetic radiation, of course, play a crucial role in our life, not only, let's say, through photosynthesis and through providing us energy through food, but also because of this we are able to see. Our eyes, through, of course, evolution, have developed based on electromagnetic radiation. A chemistry student might understand this bit more, that we have some molecules in our eyes where the light hits, and that molecule goes through a structural change from one type of isomer of the double bond to the other type. And because of this, a signal is generated and our mind is able to see through the eyes. And those molecules which are converted, they are converted back to the starting material through enzymatic process, so that we are able to continuously see using our eyes. So this evolution has taken place because there was electromagnetic radiation, right, at the first place. So we are able to see because of electromagnetic radiation. Even vitamin D synthesis happen because of EMR, and many other processes also happen because of it. So this was about natural phenomena. Of course, artificial phenomena are also there, which are developed by humans, right? For example, several devices work based on electromagnetic radiation, like our mobile phone, like a laptop. Right now, you're able to hear me, you're able to see me, of course, because of electromagnetic radiation, right? It plays a huge role in information storage, information transfer, and communication devices, and all those things. Television works because of the satellite are able to receive and send signal because through EMR, of course. So lot of devices that are there are dependent on electromagnetic radiation. Now, I think it would be interesting to understand interaction of this electromagnetic radiation with matter, right? So we have understood how they're formed, how they travel, what happens when they reach Earth, and all that. But now let's go to a bit more of like a science. What happens when electromagnetic radiation interacts with material? What happens, right? So before that, let's just go through this one simple slide where the whole spectra is represented here from gamma rays to radio waves. As you go from gamma rays towards radio waves, the energy of the electromagnetic radiation decreases, right? And there is a, you can say, direct relationship between frequency of the electromagnetic radiation and energy. So there is a one wave given at the bottom of the slide where the frequency is high around gamma rays, and the frequency decreases as you go from gamma rays towards radio waves from left to right. So frequency and energy of the electromagnetic radiation is direct relationship, while the wavelength of electromagnetic radiation is inverse relationship with energy. So as you go from, let's say, gamma rays towards radio waves, the wavelength increases, right, as you can see, but the energy decreases. So we will keep this in mind and go forward. So basically, there are several phenomena that can happen when electromagnetic radiation interact with material. But for us, three main phenomena are there to understand what I want to talk to you about. First phenomena is transmittance. Transmittance simply means that electromagnetic radiation passes through the material. Right? It goes through it and comes out from the opposite sides and continuously travels. So that is transmittance. Second phenomena is reflection. Reflection means, of course, it will bounce from a certain angle from the material, like the reflection in mirror or reflection from reflective surfaces, right? And the third phenomena is absorption, that when the electromagnetic radiation hit material, the material absorb the energy of electromagnetic radiation. Now here, before we go forward, I think it is necessary to understand the nature of electromagnetic radiation, right? We have only talked about it in the form of wave, but of course we also understand, or we have studied previously, that electromagnetic radiation exists in dual nature, right? They are wave nature and they also have particle nature. The particles of electromagnetic radiation are called photon. So photon word is basically from, you can say, I think, Greek or Latin, where phos word is used. Phos means light and on means unit. So photon is basically unit of light or unit of electromagnetic radiation. And if you recall your school study or even college study, you will realize that there are experiments that are carried out to prove both nature of electromagnetic radiation, particle and wave. So wave nature was, I think, proved through a double slit experiment, and the particle nature was, I think, proved through electric effect by Einstein, right? Where electrons were bombarded on certain radio waves were bombarded on certain material, and electrons were ejected out by the material, which were then, of course, captured and measured that those are electrons. So with wave nature, it is difficult to prove how electrons were ejected by the material, but from particle nature of electromagnetic radiation, it was easier to prove that. So photoelectric effect, that is known as, right? So these experiments proved that electromagnetic radiation have dual nature, particle and wave. So when we understand, let's say, interaction of electromagnetic radiation with material, we have to keep these in mind, right? That the photons are there in the EMR, and one photon has same energy as the electromagnetic radiation it belongs to, right? It's only the nature of electromagnetic radiation that we distinguish. Otherwise, the properties are same. And when, of course, we talk about spectrophotometry, we, of course, want to measure, right, what happens when electromagnetic radiation is absorbed or interacting with certain material. Now, of course, to measure something, we need to first detect. So there is a detector of, you can see that it is after the material, a detector is placed. Electromagnetic radiation that is passing through the material, some of it might be absorbed, while some of it might transmit and go towards detector. So in any spectroscopic instrument, detector always detects the transmitted light or transmitted waves, right? The absorbed waves are not detected by the detector. And that's why the output spectra is always a transmittance spectra, but then we are able to convert it into absorption spectra, right, through mathematical calculations, which are quite easy to do because you already know what intensity of radiation you did as an input, and then output is measured by detector, so it is easier to convert it into absorption. Now let's understand spectroscopic techniques that emerge from electromagnetic radiation. Here also our focus will be based on the energy of electromagnetic radiation and the change in the material that takes place because of this interaction. All right. So let's watch this video where different types of molecular spectra are explained. So when electromagnetic radiation is interacting with molecule, energy of molecule will increase because it absorbs the energy from this electromagnetic radiation. Depending on energy, of course, it can go from ground state of electronic energy to higher electronic energy state. Vibrational energy might increase in the molecule, or even rotational energy might increase. So rotational is the lowest, vibrational is higher, and electronic is the highest energy level. And to choose, we have, of course, the whole spectrum of electromagnetic radiation, right? So there are, based on these interactions, we have three types: pure rotational spectra, vibrational rotational spectra, and electronic band spectra. Let's understand them one by one. First, rotational spectra. A low energy radiation is used here and bombarded it on the molecule, let's say microwaves. So rotation in the molecule takes place because of this interaction, and only rotational energy increases a little bit, for which microwaves are used. Far infrared and micro are used for rotational spectra measurement. Of course, if you want to do further study, right, higher energy spectra waves can be used, let's say infrared, near infrared. Here, when molecule absorb this photon, a rotation along with vibration in the molecule takes place, and vibrational energy of the molecule increases due to absorption of these photons, right? And for this spectra, near infrared is used, and the output spectra you get is known as infrared spectra or IR spectra. The next is electronic energy excitation, for which UV and visible light is used, where electron is promoted from lower energy orbital to the higher energy orbital in a molecule. So again, of course, rotation and vibration will also happen because this is high energy waves. So basically, you promote electron from HOMO to LUMO, or you can say also you promote molecule from lower electronic energy to higher electronic energy. And of course, the measured output will be electronic band spectra, for which UV and visible light is used, and the instrument known as UV visible spectrophotometer. Right. So based on spectral region and spectroscopy that is there, for micro, we have microwave spectroscopy or rotational spectroscopy. Infrared, we have infrared spectroscopy, and visible and UV, we have UV visible spectroscopy techniques. So let's go through these spectroscopic technique, but here, of course, I will not go too much into detail into chemistry part of it, but we'll try to understand this spectroscopy with a general perspective so that all can follow, right? So for the infrared spectroscopy, which in Gujarati can also be said as Pararakta Varna Pradarsan. So infrared, the word itself is coming from the meaning of being after the color red. You can see that there is a visible portion of the electromagnetic radiation. At the last color in the visible is red, and this IR radiation is after that red color waves, right? And that's why they are known as infrared. And infrared is divided into three parts: near IR, middle IR, and far IR. This terminology is also, as you know, is based on they are near to visible region, then they are NIR, little bit away, then mid IR, and further away than far IR. And we just talked, I think, before few slides that there is a inverse relationship between wavelength and energy of that wave. So let's say if wavelength from 800 nanometer, it increases to 500 micrometer, then the energy decreases. But generally, it is easier if you have direct relationship, to talk about that phenomena, right? So this wavelength is converted into wave number. Wave number simply means how many waves are fit into 1 centimeter region, right? So that's why the unit is centimeter inverse. So for example, 800 nanometer means 12,500 waves in 1 centimeter region. So that is a wave number. And there is a direct relationship between wave number and energy, right? So wave number, higher the wave number, more energy; lower the wave number, lower the energy. And that's why it is easier to correlate when you talk about IR spectroscopy. All right, so we have, let's understand what happens when IR radiation falls onto a molecule or material, right? The exercise of the molecule happens in various ways. Symmetric stretching can happen, so both atoms symmetric stretching. Anti-symmetric means, of course, they go one by one away and close. Rocking, of course, it means this way, the movement of atoms. Wagging, twisting, and scissoring. Again, scissoring means, of course, they come close and go away from each other, right? So these are the things that happen when a molecule absorbs IR radiation, and they are known as stretching and bending vibrations within the molecule. So because, of course, the IR radiation is absorbed, we can measure, of course, right, what is absorbed. The instrument of IR works through Fourier transform infrared spectroscopy technique. And in that particular, there is a moving mirror technique that is used. And I think this is a wonderful technique. Let me just explain briefly how this works. So if you see, this is the source of IR radiation, which is a specific material. And through electric current, the temperature of this material is raised to up to 1000 to 1500 degrees centigrade. And at that temperature, it produces IR radiation. That IR radiation is passed through a filter and made parallel paths. And then these light that is parallel reaches a splitter. A splitter is nothing but a material which allows 50% radiation to pass through and 50% is reflected. So you can see that the 50% that is passing through will go towards the moving mirror, while the 50% that is reflected will go towards the stagnant mirror, sthir mirror and moving mirror, right? Why this design? You might wonder if you have not studied this, of course, technique. So when moving mirror is moving, obviously when the light comes back after reflecting from the mirror, right, from both mirrors, they will again merge with each other, and splitter will allow 50% to go towards the sample and 50% will go towards the source. So they will overlap here in this region, the lights that is coming out from the mirror. And overlapping can happen, of course, in various ways, right? The TRO can overlap on TRO and intensity will double, or TRO can overlap on the Gujaratiમાં શું કહે ગર્ત અને શૃંગ, right? If they overlap on each other, then they nullify each other and it becomes zero intensity of the wave. So using one wavelength, you are able to use intensity between 0 and 2 through moving mirror mechanism, right? This IR radiation is then passed through the sample. So sample is kept here. Some of it will be absorbed and the non-absorbed radiation will reach the detector. Detector records the transmitted radiation and gives interferogram. Now this interferogram output, of course, does not provide us information directly, but it is converted into a spectrum through Fourier transform. It's a mathematical transformation which converts interferogram output into spectrum. And the spectrum is, let's say, a transmittance spectra. And from the peaks that you see at specific centimeter inverse, you can say characterize the molecule from the functional groups that they are present in the molecule. So basically, IR is used to determine functional groups that are present in the material, right? For these, basically two techniques are there to measure IR. One technique is KBr pellet method, where KBr, that is potassium bromide, it's used. And some, I think 10% or 5% of compound is added into KBr. And in the mortar pestle, they are grinded together to make a powder. And this mixed powder is then taken into a pellet maker. And pellet of KBr containing compound is formed. So of course, here there are photographs of pellets you can see. The first one is excellent and that can be used directly for analysis, while the other ones have some issues, right? Can be cloudy or that can be defective or with scratch or broken. So those cannot be used. So KBr pellet making requires a nice handling technique. And if you are able to form excellent pellet, then only you can use it to analyze it through IR. Right? And then sample holder is there where the KBR pellet is put, and then that is put into an instrument and measured for the IR absorption. So here you can see that KBR is required, high purity KBR is there, and then you have to make pellet, and then it requires a lot of manual effort, right? So there is another technique that is there in the FTIR, and that is attenuated total reflectance. So attenuated total reflectance technique uses a crystal of certain material which has 100% reflection capacity. So IR is coming from the source within the instrument, and it hits the surface from inside, and it is 100% reflected. So when a wave is 100% reflected from a surface, evanescent wave is created in the opposite side. And this evanescent wave can be absorbed by the sample, and we can measure IR. So sample is just put onto the crystal without any treatment, right? You don't need KBR. You can directly use a solid or liquid sample, put it on this crystal and measure IR. So it is as simple as that. And the instrument looks like this. We have this instrument in our department here, which is from Bruker company, and you just have to put sample on this crystal, which is here. Just a little bit of sample, 10 to 20 milligram is enough, and you can measure IR within a minute, right? So it's very fast technique. And basically this is what happens when IR radiation is absorbed by molecules. So this is example of ethanol molecule, and you can see that there is bond stretching is happening when a certain frequency is hit, right? OH bond is elongated, CH bonds are elongated, and then C single bond O is elongated. So vibration is happening in the bond, right? And that is measured by the instrument. This technique can be used basically to understand the functional groups that are present in known or novel material. Let me skip some of this chemistry related part. This might be interesting for you because this is a soap making technique. So you, I think, all know that how the soap is manufactured, right? So generally oil is used for that, and saponification technique is carried out where NaOH, that is sodium hydroxide, is mixed with oil. Hydrolysis of the ester of oil takes place, forming glycerol and sodium fatty acid. So basically sodium fatty acids are the soap or sabu jene apne kahiye, right? So this reaction can be monitored through IR. You might wonder how. So during as soon as the NaOH is added into the oil, there can be a kind of a probe that can be inserted into the reaction, which can measure the IR absorption through that reaction. And here in the graph you can see that the CH bond stretching is disappearing after 30 seconds, while the OH bond stretching is increasing after 30 seconds. So the glycerol is formed completely, and CH bonds are changed because the starting material is no longer the same, right? The product has formed. So through this IR probe instrument, reaction progress can be monitored each second. So it's quite interesting application of IR. One of my PhD student, Dr. Shiv Desai, who completed his PhD last year, and he already got the degree in the convocation as well in December. He prepared some ligand molecules which had phenolic OH groups. And when he made metal complex of those ligands, you can see that in the ligand spectra that is in red had OH stretching at 3620 centimeter inverse. And when the metal complex was formed, that peak disappeared. So this proved that the OH is no longer present in the complex. So this was helpful in understanding whether the reaction was completed or not. Similarly, another PhD student who is doing PhD under my guidance, Vidhi Bhopekar, she did a conversion of cyanide group into CONH2, that is amide, benzamide functionality. And here also CN stretching peak was observed at 2225, which disappeared completely when the molecule was converted from cyano to amide or benzamide, right? So here again, IR was helpful to confirm that the reaction has completed. So IR is kind of a complementary technique. It's not like giving you complete idea about the structure of molecule, but it helps in determining functional groups, basically speaking, right? Then comes UV visible spectroscopy. So in the UV visible spectroscopy, ultraviolet and visible light region are used in the instrument. So UV basically means from 100 to 400 nanometer, while visible means from 400 to 800 nanometer in terms of wavelength, right? And these both regions are used together. Now, let me tell you a little bit about this. First, let's go through the instrument, and then we can talk about what basically happens in the molecule when UV or visible light is absorbed, right? So there is a source that can be D2 lamp or tungsten lamp, and through which the UV or visible light is produced, and then through a mirror it goes through a filter, and then it goes through a beam splitter, which will allow 50% to pass through sample, while 50% will pass through reference cell. And then, of course, detector will detect what is coming out from the sample and reference, and then give you output absorption spectra. And this is based on Lambert-Beer's law or Beer-Lambert's law. The concentration of sample and path length is directly proportional to the absorbance of light. So based on this equation, absorbance is measured by the instrument. Now, when we talk about, let's say, material, of course, materials have different colors, as you know, right? Material can have red color, or it can have white color, or black color. What does it mean to have color? Why do we see certain color with certain material, right? Why is, let's say, some color is blue, some is red, or some is orange? Because that material has property to absorb a certain type of wavelength from the visible spectrum, and it only reflects the wavelength that we see, right? For example, if something is of red color, that means red color is reflected by that material, while the rest is absorbed by that material from the visible spectrum, right? Black absorbs everything, while white reflects everything, right? And because of this, we see color. So for this property of material, that it absorbs, let's say, certain wavelength and reflects certain wavelength, these properties because of the structure of that material, molecular structure of that material, where there can be chromophore groups, functional groups, which are responsible for the color, while there can be also oxochrome groups, which enhance or decrease the color intensity of that particular material. An electronic transition that can happen in the material can be represented by n to pi star, pi to pi star, n to sigma star, and sigma to sigma star. From what you have studied, let's say, in your 12th science education, you might remember that there are molecular orbitals in material, bonding and anti-bonding. So sigma and pi are bonding orbitals, while pi star and sigma star are anti-bonding orbital, while the n is non-bonding orbital, right? It did not make any bond, but electrons are there. So, of course, electrons can be promoted from the filled orbital to the empty orbital. So, bonding orbitals are filled orbital, and anti-bonding orbitals are, of course, the empty orbitals. In other terms, you can say electron is promoted from HOMO to LUMO when it absorbs photon from UV or visible radiation, right? Let me skip some of the chemistry part again, and let me take you to application part, so it will be more interesting to the general crowd. So my second PhD student, Dr. Shiv Desai, he synthesized these nitrolophin compounds and developed wonderful applications, where you can see that if nitrolophin is taken in DMSO solvent in neutral condition, it is red in appearance. If base is added into this, if the solution becomes basic, then it gives purple color, and if the solution becomes acidic, it gives yellow-orange color. So this type of material which change color with change of pH are known as halochromic material, and they are used in titration experiments, and several other applications are there. So here in these vials you can see that the same concentrations, one compound is kept into DMSO, and the pH is kept from 1 to 14, and you can see that the color changes, right, from non-color to yellow to orange, red, and then completely purple at the end in the basic condition. An UV spectrophotometer instrument, which is presented here, was used to determine UV of this compound at different pH value, is represented here in the spectrum. And let me show you a wonderful application of this compound. So what Shiv did is he put this compound onto a filter paper, and then this paper was dipped into basic solution and became red. Then it was washed in water and then put in acidic, and the color disappeared. So it was done reproducibly, right? You can see wonderful application of this compound on paper. So this is basically nothing but a pH paper, right, which you might have used in a lab, where pH is measured through just dipping the paper. So this was reproducible up to 5 times without loss of effectiveness, you can say. So again, pK values can be determined through measuring UV at various pH and using Henderson-Hasselbalch equation. So this work was patented. So we have filed a patent which is published, and we are awaiting for the grant of the patent. And work was published in Journal of Photochemistry and Photobiology A, Chemistry, in 2025 or 24. Another work that Shiv developed was this molecule, which is a dye, azodye molecule. And interestingly, when this is taken into DMSO solution, it gives different color with several metals. You can see here that if Fe is added, it becomes orange. If copper is added, it becomes light orange. Aluminium, it becomes lighter colored. Nickel, color is completely disappeared. Zinc and copper, it becomes purple under alkaline conditions. And again, with cobalt also, there is a slight color change. So this is an application of metal detection, you can say, in samples, right, in soil sample or other samples. So single molecule detecting 7 different metals with a visible naked eye color change. So this was possible to develop because we have, of course, had a UV spectrophotometer, right? We were able to measure the UV absorptions of the ligand and also with different metals. So this work was also published in 2025 in Spectrochemica Acta Parte, and we have also filed for a patent for this work. Similarly, another dye molecule was prepared, which was halochromic in nature. Let me just directly show you the application again. So this dye was put on a paper, and then that paper was dipped into, let's say, first NaOH, it became brick red, and then again in HCl, the color disappeared or became lighter tone. Again, when it was put back into base, again it became brick red. So again, this dye was useful as a halochromic dye. You can imagine application in the terms that, for example, if this dye was put on a paper or on a cloth, textile material, it would change color with change of pH, right? So that can have a lot of applications. We also developed a gel with this dye, which was changing again color under basic and acidic conditions. So I'm showing you the application of UV spectrophotometry in my own research group, right? So that you can understand how it is valuable. The next technique is fluorescence emission spectroscopy. So in this spectroscopy technique, uh, what is measured is fluorescence, you can say. So let's understand what is fluorescence. For that, we first have to understand the singlet excited and singlet ground state of a material. So in the ground state of a material, electrons are paired, total spin is 0. And when you use equation that is 2s plus 1 to calculate spin multiplicity of the species, s is the total spin here, which will be 0 in singlet ground state. So the answer will be 1 of this equation, and that's why the material is considered in the singlet state. If you promote one electron to empty orbital through, of course, UV or visible radiation, still the spin will remains opposite for both electrons. And that's why the total spin is still 0. And that's why the material is still in the singlet state. But the previous one was singlet ground state, while this one is singlet excited state after promoting electron. Now, if, let's say, electron spin changes here, then you will have, of course, 2 electrons with same spin. So here the total spin is 1, because for one electron it is plus 1/2, for the other it is plus 1/2. So total spin becomes 1, and when you put that in this equation, you get answer as 3. And this state is called triplet state. So fluorescence is basically when molecule from singlet excited state go back to the ground state and emit all the energy in the form of light. That is known as fluorescence. Right, you can understand it from this representation. So molecule is in the ground state, it absorbed photon, it went into the excited state, then it loses some energy through vibrational cascade, non-radiative transition, you can say, and it comes into singlet excited state. From here it will just emit all the energy in the form of light and come back to the ground state, and this is basically fluorescence. So when you compare absorption and emission, there is a slight difference in energy, right? Because some energy is lost through non-radiative transition. And that's why the emission spectra is always at a longer wavelength compared to absorption spectra peaks. Let me just go forward and show you some applications because it might be more interesting to the general crowd that is present in the audience, right? So fluorescence, as I said, when material absorbs UV, it emits fluorescence. When there is no UV, it does not give any radiation back. So which can be understood from this example of argonite fluorescence that is observed in argonite crystals. So my PhD student Vidhi developed some compounds which are cyanolophenes, which are fluorescent in nature, and you can see here that they are filled in these vials, and visible in visible light there is no fluorescence on the top photograph. In the middle, it is under sunlight, and you can see that there is fluorescence, right? And the bottom one is under UV radiation in a cabinet where artificial UV radiation is used, and you can clearly see there is fluorescence. And interestingly, at different pH, the fluorescence is different, right? In acidic and neutral pH, the fluorescence is blue, while under basic pH, the fluorescence is green colored. So again, this material is halochromic, but now not visibly, but under UV. So fluorescence application comes into picture. So these are the molecules that represented that particular phenomena. And you can see here that in the middle flask, when base is added into the flask and it is stirred, it gives green fluorescence, right? So this was measured in a UV cabinet to represent this transformation. Another application that we developed was inkless secret message writing material using these particular compounds. So on paper, we wrote something, and you can see that you don't see any message on the paper, right? Paper looks blank. But as soon as the UV light is turned on, you will see the message, right? My institute name initial TICS. So when this is dipped into basic solution, it becomes green colored. And when it is dipped into acidic solution, it again becomes blue fluorescent. So we could develop this application because we had a spectrophlorometer and we could measure properties of this material that was there for this type of compounds. We did is use these compounds and we took, let's say, fingerprints on different surfaces, and using a powder dusting method, we applied our compound on the fingerprint. Visibly, of course, there was not much color, but when we used UV light to visualize these fingerprints with our compounds, we could clearly see the fingerprint on 6 different types of surfaces: glass, spatula, metal, booklet, even aluminum foil, a Ziploc bag, polythene bag, right? So you can see that once you have, let's say, one type of application of a material, you can expand it to various types of applications. So this work was published in Journal of Molecular Structure in 2025, and we have also, of course, filed for a patent for this work. These are the unpublished results, and let me quickly take you through these results. So again, we developed new molecules. I will not disclose the structure here because we have not published those compounds yet. But similarly to the previous case, when, let's say, base was added into these compounds, they give green fluorescence. When acid was added, they give blue fluorescence. You might wonder how it is different from what I have already presented to you. Let me just go through the different applications that we have developed. So here what we have done is that using these new compounds, we have developed, you can say, application in terms of what we call is stamping. So if we use, let's say, this compound for stamping, you don't see anything with naked eye on paper. But as soon as this paper is put under UV, you see the stamp. And when this stamp is dipped or pH of this, let's say, material is converted into basic, then it gives green fluorescence. And reversibly, if acid is put into this material, it becomes blue fluorescent. So you can imagine there is a lot of application for this particular material. Even with ink, if the compound is added into ink, then you see a normal stamp in visible light. But as soon as you put it under UV, you see it as a blue fluorescent ink. So it has a lot of applications in currency notes, in document verification. Authentic documents can have this type of, invisible stamps, which can only be visible under UV. So you can understand there is a lot of application for this type of materials. All right, I think up to this part, I had a general type of talk, and onwards, it is more specific to chemistry. So I would not present that to you. Let me just go through it. So this is about NMR, nuclear magnetic resonance spectroscopy. and how it is applicable and how it was useful to me in my research and my current group research. But I will not, I think, present it much as it is specific to chemistry. Let me just talk about this particular slide for chemistry students. So this molecule which was synthesized, uh, NMR at room temperature, that is at the bottom, had strange peaks. You can see the peaks are quite broad, and it was not possible to understand what NMR wanted to tell about the compound. Well, the compound was pure, right? So it was a bit surprising, but I knew that rotamers are possible in this type of compounds. And if you increase temperature in NMR, then the peak spectra, there is clear splitting pattern in these spectra, clearly indicating that this compound were present in rotameric mixture. And as the temperature was increased, rotamers disappeared and only one diastereoisomer was there. All right, I will just skip the rest of the things. And let me come to the last slide, that is for acknowledgement. So because I presented some work that I carried out in the Professor Thorsten Bach's group in Germany as Alexander von Humboldt Fellow, I am acknowledging him here. Well, this is my group currently. So there are currently 8 students working under me. Rinkel, who is here, has already completed her PhD. She was my first PhD student, while Shiv Desai here has also completed his PhD. The rest are currently doing their PhD under my guidance. Mahesh Kolodia working at Ether Industry, Gunawantbhai Dudhagra, owner of Rhodium Master at Rajkot, and then Viral, Dhruvi, Reena, and Subhas, they are working at Piramal Industries. Well, these 2 students are working full-time PhD under my guidance right now, Vidhi and Bharvi. So I am thankful to, of course, their efforts. Because of their work only, I could present these applications of spectroscopy to you. And I'm also thankful to Professor Dr. Naval Kapuria for inviting me to present this work here. I must apologize that I did not know the crowd will be a general crowd. Otherwise, I would have prepared the talk accordingly. So I thank you all, of course, and look forward to any questions you might have. Thank you.
Thank you, sir. Thank you very much. Yeah, first of all, your journey looks too much positive. जो आपने पहले बोला था कि भाई मैं या
Yes.
12 साइंस में इतना था,
Thank you.
फिर फर्स्ट ईयर में इतना था, but it's a symbol of positive, sir. So I would like to thank to you for the session as well as also for the fruitful lecture. Okay, thank you very much, sir.
Thank you. So I hope it is done. Yes.
Yes, sir, it's done, sir. Okay, thank you, sir.
Excellent. All right. Thank you. Thank you very much.
Okay, welcome, sir.